Properties of logarithms. All right, so before we get into these really fun, cool properties that logarithms have, which they really are a lot of fun, I want to remind everyone of our loop-de-loo method of switching a logarithm into an exponential and an exponential into a logarithm. Just quickly, just in the margins of our paper up here, we'll even use a fun color like purple. So if you have something like log base A of B equal to C, to change this into an exponential, remember, start at the base, across the equals, back again. It's our loop-de-loo method. One more time, the phrase is start at the base. So the base in the logarithm is the base of the exponential. Right? This is my base. Start at the base, across the equals. So raised to the C, because that's the next part we would write. If this is the base of the exponential, it needs an exponent. And back again is equal to B. Knowing how to do the loop-de-loo is going to be incredibly important for all of properties of logarithms and also for the next section where we talk about logarithmic equations and exponential equations. It's really important that you know this loop-de-loo method. It's easy to get down and it works in both directions, right? If I did something different, let's do another fun color. We'll do green. If we did something like x raised to the y is equal to z, if I want to switch this into a logarithm, I'm starting at the base. So the base of my logarithm is x. Log base x of, across the equals, log base x of z is equal to, and back again, y. Right? It works in either direction. Start at the base, across the equals, back again. Cannot emphasize this enough. All right, so keep that all in mind. So logarithms are super, super cool. There's so many fun, cool applications of logarithms. I'm excited to talk about them. There's 7 big important ones, and they are listed on this page. And I want to go through a few examples of them, talk about them in a little bit more detail, and then we'll be using these properties to do fun things with logarithms, like break them up into a bunch of different pieces, which may not sound super fun now, but once you get to calculus, so important. All right, so here we go. So first property of a logarithm is that regardless of your base, right, it doesn't matter what base you have, log of what base whatever of 1 is 0, always, no matter the base. For all bases, this is true, right? We start at the base, B. You know what, this is gonna get crowded in here. We'll start over here. We'll do an example over here. I'm just gonna put a base on here. Let's do base 3. Log base 3 of 1 should be 0. And why? Well, start at the base, 3. This is because 3 across the equals raised to the 0 is equal to 1. Yeah, that's true. Anything raised to the 0 is 1, except for 0 itself. All right, 0 to the 0 is indeterminate. That's a different case. So when I say anything raised to the 0, I don't mean 0 itself. But that's the reason that this rule exists. If you plug 1 into a logarithm, you're going to get 0. It doesn't matter what the base is. You can make the base something generic like base B of 1 is equal to 0 because B raised to the 0 will be equal to 1. So log base B of 1 is equal to 0. If you take the log base B of the base, so log base B of B, you're going to get 1, no matter the base, for all bases. So if we use an arbitrary base here just to prove this to ourselves, let's say we have base 4, log base 4 of 4 should be equal to 1. Why? Well, start at the base, across the equals back again, because 4, the base, raised to the 1, is equal to 4. Yeah, that's true. And that's going to be true no matter what that number is, right? Log base b of b should be 1. Start at the base, across the equals, back again. Because b raised to the first power is equal to b. This is always going to be true. It doesn't matter what b is. Anything raised to the first power is itself. That was an exclamation mark, but I'll just get rid of it. Anything raised to the 1 is just itself. All right, these next two I find that students don't like as much, and it's because they look a little messy. So one thing I want to point out about number 3 is that all of this right here that's highlighted is in an exponent. Log base b of x is in the exponent. In the exponent of b. So it's like we have b raised to all that stuff that's in, that's been highlighted here, right? So this is b raised to the log base b of x is equal to x. And we should ask why. Why is this true? So let's look at an arbitrary base so that we can see why. I don't know, let's choose the number 2. It seems like a good number. So is 2 raised to the log base 2 of x equal to x? Let's do our loop-de-loop. So start at the base. This is going to be a logarithm base 2, log base 2 of, so across the equals of x, and then back again, is equal to log base 2 of x. Oh yeah, that seems logical, right? Log base 2 of x is equal to log base 2 of x. That checks out, right? That's why this works for any base. It doesn't need to be 2. It could be whatever base we want. When we go to do our loop-de-loop, start at the base, across the equals, back again, we get that log base b, right, start at the base, across the equals of x, and back again, is equal to log base b of x. This also works because exponentials and logarithms are inverses of one another. So when you compose a logarithm with an exponential, the two ideas cancel each other out and leave you with just an x. Right? It has to do, the reason this happens is because the two functions are inverses of one another. Number 4 is the reverse of number 3. So it's still using the property that logarithms and exponentials are inverses of one another, but it's plugging an exponential into a logarithm. So let's prove to ourselves that this works, that log base b of b raised to the x is equal to x. We know that log base b of b is 1, but log base b of b raised to the x, this is a subscript, regular script, superscript. So we ask ourselves, why is this true? Well, what's a good number? I don't know, 7. I like the number 7. Let's do log base 7 of 7 raised to the x equal to x. Let's see. All right, start at the base, 7, raised to the x is equal to, back again, 7 raised to the x. Yeah, that all checks out. 7 to the x is 7 to the x. This is true because when we rewrite it, it comes from a true statement in the first place. Rewriting the statement 7 to the x equals 7 to the x as a logarithm results in this statement right over here. So going in the backwards direction, we get the same thing. Do our loop-de-loop, start at the base, across the equals, back again. Ask me how many times in my life I've said that because it is a large number. B raised to the x is equal to b to the x. So this will work with any base, right? All of these work with any base. That's why it's a generic B. numbers 1 through 7 are true of all bases. And there's the proof. All right. So those are really fun ones and they have lots of applications. They really do. But my favorites are number 5, 6, and 7. All right. My favorites are number 5, 6, and 7 because it takes everything that we know about math, that we've trusted about math, and it becomes not true anymore. And exponentials just say, oh, now throw that out. I work different. Things work different around here. So that's what happens. So when you have a logarithm, base whatever, and there's an exponent on whatever's inside the logarithm, right? This whole thing is like inside the logarithm. We can take that exponent and we can bring it down out front. That's what's happening. This exponent, c, gets brought down out front and multiplied in front of the logarithm. This is really cool. All right, this is super cool. Let's do an explanation of this. Right. So let's say we have log base 3 of x raised to the 7. Right. Did I just say we're going to give a reason for why this works? I had to pause myself. We're not going to give a reason for why this works. That's not, there's not time in this video to give explanations for these last 3, but I'm going to show you how it works. I do these all in one take, guys. If I mess up in the middle, that's all there is. Like I video editing is a skill that I will develop in the future that I don't have now. Anyway, here's what we have. We have log base 3 of x raised to the 7. What we can do, we can take this 7 that's on the inside here, and we can move it out front. So it becomes 7 log base 3 of x, right? Log base 2 of 12 raised to the 13 is equal to, you can bring that 13 down in front. 13 log base 2 of 12. So just small cautions here. All right, just have a tiny bit of caution. It's super cool because that doesn't work like anything we know or love. But now we can love this. It doesn't work like things we're used to, but you have to be careful because it does have a little bit of a but here. The exponent needs to be on the entire inside. So here's what we can't do. This is a no. Right? I'm about to write something that we cannot do. Right? So if you have log base 2 of xy squared, this square is only on the y. It is not on the x. So we cannot bring that 2 down in front. Right? These are not equal, not equal. I'll even write the word not equal just so there's no ambiguity. All right, we can't bring that 2 down because that 2 isn't also on the x. We could bring it down if there were parentheses and xy was all being squared, but otherwise we cannot bring that 2 down. So keep that in mind. All right, first important property. These last 3 are about to be used a lot in this section. Property number 6. If you have multiplication on the inside of a logarithm, you can split up the logarithm into 2 different pieces with addition. So the way I like to say it is multiplication on the inside turns to addition on the outside. On inside, addition on outside. All right. So I like to think of like, multiplication. That's a multiplication symbol. And this right here is like an addition symbol. So like they look very similar. So I think multiplication on the inside means addition on the outside. So as an example of this, and this works for any base, right? Log base, I don't know, 8. I haven't used 8 yet. Log base 8 of 5x. Here we have 5 and x being multiplied together, right? These are being multiplied. I can break this up into log base 8 of 5 plus log base 8 of x. If I have log base 2 of xy squared, like I did above in that example right here, these x and y's are being multiplied together. So I could break this up into log base 2 of x plus log base 2 of y squared. So multiplication on the inside turns to addition on the outside. I guess I had room to put this over here. On the other hand, if you have division inside of a logarithm, it turns to subtraction on the outside. So if I'm dividing m and n, I can split this logarithm up into log base b of m minus log base b of n. And again, this kind of has a nice logical memorization trick built in because division has like a minus sign right inside of it, right? This is my memorization trick. Multiplication turns to addition, division turns to subtraction. And so over here, let me write that down. Division on inside, subtraction on the outside. So, I mean, how many examples can I give here? Let's do log base 4. Log base 4 of 12 divided by x. This will be log base 4 of 12 minus log base 4 of x. These are the rules. These are the rules. Now, one thing I want to point out here is that especially rules 6 and 7 can be easily misinterpreted, right? Addition on the inside of a logarithm doesn't do this, right? If you have log base b of m plus n, this doesn't do anything, doesn't break up, doesn't simplify. Addition on the inside or subtraction on the inside, that doesn't do anything. It does something when there's multiplication or division on the inside. Multiplication or division can change into addition/subtraction, but addition on the inside doesn't turn to multiplication on the outside. So if you have log of m minus n, this doesn't simplify. Right. So this applies to any base. Here's all the rules, nice and simplified here. This applies to any base. And in particular, I want to remind us of base 10 and base e. So here in base b, this is just a generic base. When we make our base 10, when we let b equal 10, instead of writing a 10 for the base, we just write log. So whenever you just see a logarithm, it's base 10 immediately. And when our base is the natural number e, log base e, we don't write log base e, we instead write ln of x. So this is when the base is e. So these look a tiny bit different with these different bases over here. Let's just write them out quickly. So log base b of 1 is equal to 0. If we did that with a base 10 log with the log notation, that would be saying that log of 1 is 0. Log base b of b equal to 1, if b is 10, that means that log of 10 is 1. Remember, we don't write the base 10 here because when it's base 10, we omit it. Okay. B raised to the log base b of x is equal to x with a base 10 logarithm would be that 10 raised to the log, don't need to write the base, log of x is equal to x. Log base b of b to the x is equal to x. And now would be a good time if you want to pause and try these out, try the rest of them. Now would be a great time for that. This guy right here, log of b is 10 raised to the x is x. The bring down the exponent rule becomes if you have log of x raised to the c, this is c log x. Bring down the exponent. For number 6, if you have log base 10 silently of m times n, this becomes log of m plus log of n. If you have log base b of m divided by n, with base 10, it becomes log of m divided by n is equal to log m minus log n, right? These last three are literally just kind of like omit the b, right? The last three is just omit the b because log base 10 is just log. The top 4 ones, you have to keep in mind the base because the b changes. There's other instances of the b, but that's in base 10. If you're up for a challenge, now would be a good time to pause and try the base e. All right, trying the base e by yourself. So not writing it as log base e, right? Not just simply doing all of these with an e instead of a b, but using ln instead of log base e. All right, so this would be log base e of 1, but log base e, just this part is what I wanted to highlight. This thing here is the same as this thing here. So wherever you would have a log e, you should have an ln instead. So instead of log base e, this would be ln of 1 is equal to 0. Log base e of b is 1. This is ln of e is 1. E raised to the log base e of x is x. E raised to the ln x is x. So e and ln essentially cancel each other out. You can really think of it as like they cancel. Log base e of e to the x is ln of e to the x. So ln of e to the x is x. Again, it's like the ln and the e cancel each other. And then these last rules are legitimately just, instead of log b, you write ln, because these rules aren't as exciting. So if you have ln of x raised to the c, it's c ln of x. If you have ln of m times n, this is ln m plus ln n. And if you have m divided by n, you have ln of m minus ln of n. And that is our intro to the basic properties of logarithms. In our next section, we're going to use these rules to split up logarithms, expand them. We're also going to combine them. It's going to be a lot of fun. We're really going to be relying on these last rules a lot in this section, but we will also be using these ones here. So there's that. I will see you in the next video, and we will continue our discussion on logarithms. Bye.